In this video, we'll talk about resistivity and conductivity. The resistance of an element is an extensive property. As we've talked about previously, an extensive property is a property that depends on how much of something that you have. For instance, mass is an extensive property. It makes no meaning to say, what is the mass of carbon? You can ask, what is the density of carbon? That has a well-defined meaning. But the mass of carbon depends on how much carbon you have. So we want to be able to write things in terms of intensive properties, that is, things that don't depend on how much you have, so that we can put these inside of tables. Resistance isn't that way. It depends on the geometrical factors in which you make a resistor out of. So if you want to find the resistance, it depends on geometry, that is the length and the area. So it's extensive, and it also depends upon the temperature. Now, there is an intrinsic property, at least for a given temperature, and that's called the resistivity, which is related to resistance, but not the same thing. It's much like density is to mass, where we've taken out this kind of geometrical shape stuff out of the problem. The relationship between this intrinsic material property called resistivity and resistance is the following formula. The resistance of an object depends on its resistivity, its length, and divided by its area. So this is the cross-sectional area. This is the length, and this is the resistivity. So if you build something, say a bar, or it could be a wire, doesn't matter, you can change the amount of resistance by changing the length. If you make it longer, it'll have a greater resistance. You can reduce its resistance by increasing the area, or you can make it go up by decreasing the area. And you can change the material you make it out, which changes the resistivity. So you can make a resistor of any value you want if you take an ohmic material of a known resistivity and you just adjust this length and area. Now the conductivity is the inverse of resistance. So conductivity is 1 over the resistivity. Now, there's also conductance. And conductance is generally considered to be 1 over the resistance. Kind of interesting, conductance has an interesting unit. Its units are the mho, which is just ohms spelled backwards. It's 1 over ohms. That's conductance. The conductivity has the units which come from the resistivity units, which I guess I should tell you back up here. The resistivity units, if you look at this thing has ohms. This has a length, meters, but it's divided by a meter squared, so this thing has to have an ohm meter. So the units are ohm meters. So the inverse of this would be ohm meters to the -1, which of course would be a mho per meter, although you don't tend to see mho per meter very often. You tend to see it written like this, inverse ohm meters. Let's give an example of where you do this. You're required to construct a 2 ohm resistor using a carbon rod. Some years ago, when I was a student, I had to build a project to measure some very thin wires as they were busting due to what's called electron migration. The electrons would come in and hit, knock out atoms, and it would cause the the lines to fail in integrated circuits. And they wanted to do what was called accelerated testing. Wanted to figure out how long this chip would last by heating it to speed this up so we can measure in a small time. Unfortunately, you had to stay there day and night, and so we needed to build some way to measure this. And I built or designed a circuit, but I needed some resistances. There were only milliohms of resistance, and you couldn't buy them. And I ended up making them by making my own with some carbon rods and using a pool of mercury inside of a little plastic container that I got from one of these gumball type things that you put a quarter in. Anyway, you're required here to construct your own 2 ohm resistor, and you're using a carbon rod with a cross-sectional area 1 by 10 to the minus 2 centimeters squared. How long must the carbon rod be? So here's a resistivity, 3.5, 10 to the minus 5 ohm per meter. You get that out of a book. And then you're looking that the resistance is equal to the resistivity times the length over the area. You simply need to now convert that over to length is equal to resistance times area over resistivity. So length is equal to 2 ohms times 1 by 10 to the minus 2 centimeters squared, but I need to get that in meters. So I have 1 meter per 100 centimeters, and I need to square that. And then I need to divide by the resistance, and the resistance was 3.5 times 10 to the minus 5th ohm meters. So if I've done that right, the centimeters are canceled. One of the meters here cancels one of the meters up there. So I'm still left with a meter, and this ohm cancels that ohm. And we just punch it in a calculator. So 2 second e to the minus 2 divided by 1 second e to the 4 divided by 3.5 second e to the minus 6. I'm sorry, 5. And I get that it is 5.71 centimeters. So 2.5 centimeters per inches, you need about a 2-inch long, a little over 2-inch long rod of carbon. All right. Next thing that we might look at is the fact that the temperature can affect both resistance and resistivity. As the temperature increases, the resistance or resistivity of most materials increases. And the way to think about this is that these little electron guys are flying along like this, and there's these atoms throughout the material, and these atoms are vibrating back and forth, and they're vibrating kind of like doors opening and closing, and this electron or whatever this charged particle is trying to get through this barricade, and it's getting scattered. And the faster you move these, the more likely it is to bang into them and cause it to scatter out of the way. Now that's certainly a classical way, but it does explain why, if these guys are moving back and forth, that it's harder for the current to get through, and therefore the resistance increases. Now, there's lots of ways to show the mathematics. It's really not necessary here. It's enough to know that to find the resistivity at a different temperature, you just need to know it at one temperature, and then you need to multiply that by some alpha times delta T. Now, different books do this slightly differently. Some books, the alpha that they give you has got to be multiplied by rho naught, and in other textbooks it does not have to be multiplied by rho naught. So it kind of depends on your particular textbook as to which way it chooses to go here. This alpha is called the temperature coefficient of resistivity, and it's different values for different materials. But basically it says that this is simply rho naught plus alpha rho naught times delta T. If you look at this, this looks very much like what we did when we had thermal expansion, and there's a reason for that. It's the same math technique that gets us this formula. Now you likewise can do the same thing for resistance. So let's do a calculation here. It says we have for silver, they want to know the resistivity at 100 degrees. Well, I know it at 20 degrees. It's 1.47 by 10 to the minus 8 ohm meters. And they tell me alpha is 3.8 times 10 to the minus 3 centigrade to the minus 1. And I know that delta T is 100 C minus 20 degrees C, so that's 80 degrees is delta T. So rho is 1.47 by 10 to the minus 8 ohm meters plus 1.47 times 10 to the minus 8 ohm meters times 3.8 by 10 to the minus 3 centimeters, degrees Celsius to the minus 1 times 80 degrees Celsius. That Celsius kills that. I'm still in ohm meters. Punch this into a calculator. The change is 0.304, and I add that to 1, so it's going to be rho naught times 1.304, if I've done that right. And then we multiply it by 1.47 second e to the minus 8, and we get a resistivity of 1.92 by 10 to the minus 8 ohm meters. So it has gone up, and you're able to find the value at that particular temperature. All right, that completes this video.